Okay, this is Physics 112, Chapter 19. This is Lecture 11. And we are going to talk about electric potential and electric field. So, in mechanics, we always talk about gravitational potential energy. Let's suppose an object is at a height h above the ground. This is mass m at point A, and we say that the potential energy of this object at point A is mass times g times height h. Okay, so that's the potential energy at point A. Okay, now let's suppose I want to make this object drop a distance x, right? So let me draw another picture. So now this is the original height, and then this is a distance x, right? This is point A, this is point B, and this is the original height h. So obviously this new height will be h minus x, right? The whole height is h. It has dropped a distance x, so the new height is h minus x. So now let me calculate the potential energy at point B. Potential energy at point B is equal to mg, and the height is h minus x. So when it drops a distance x, why does it drop? Because the gravity is pulling it down. That means gravitational force has done work on that object, and the work done is, you all know, work done is force times distance. The force is mg, and the distance it has dropped is x. So the work done is mgx. Let's look at the potential energy difference. Potential energy difference between these 2 points is the change in the potential energy is the final potential minus initial potential, which is at point A. The final potential energy is mgh minus x minus initial potential energy is mgh. So I have mgh minus mgx, mgx minus mgh. So this mgh and this mgh cancel out, so I get negative mgx. So we see that work done, which is mgx, and change in the potential energy is negative mgx. So work done must be equal to negative delta PE. And this is true for all conservative forces. For conservative forces. What are conservative forces? Let's suppose if you want to go from one point to another, let's say like in gravitational field, then it doesn't matter which path you take to go from one point to another, the amount of work you have to do is the same. Amount of work you have to do is the same. So the work done to go from point A to point B is independent of the path that you choose. Then that type of force is called conservative force. So gravitational force is one of them, and electric force is also one of them. It's also a conservative force. So for electric force, then we will also write W is equal to negative delta PE. Now as you can see, that delta PE depends on the mass m, so in our case it will depend on the charge Q. So let's suppose, in order to see how similar it is, let's draw a positive plate, and then I'll draw a negative plate here with negative charges on it. And just like in your book, I'll make a little gap so you can imagine this charge will be accelerated through this little gap. So this little charge has charge Q. Then when it goes from this point A to this point B, then electric field will have done work on it. Then the work done will be equal to negative change of delta PE. Okay, so we will see that. Let's suppose, what is the work done on this object? Again, work done is force times distance. Let's suppose the distance is d here. Then what is the force? For a charged particle, the force will be electric magnitude of electric field E times charge Q, and then the distance d, so that's the work done. So you see, work done is equal to negative delta PE, and again delta PE, or potential energy, will depend again on the charge Q, just like for gravitational potential energy, it depends on mass m. For electric field, it will depend on the charge Q. So we want to define electric potential independent of this charge. So what we do is we will define a concept called potential, electric potential. Electric potential, and we will use the symbol V, and V will be equal to potential energy divided by Q. So then the potential difference between A and B is potential difference VB minus VA will be potential energy at B by Q minus potential energy at A divided by Q. Then it will be independent of Q. So it will be delta PE by Q. But work done is always given by W is equal to negative delta PE. Okay, now let's go to page 2. So now I want to define a concept called electron volt. So electron volt is a unit, and we write E with a capital V. Little e and a capital V is called electron volt. So if I want to write million electron volt, I'll write MeV. And if I want to go giga electron volt, I'll say GeV. Okay? All right. Or if you want kilo, then it'll be KeV. All right, so these are just names, but as long as you understand what electron volt is, that's good. So electron volt is defined like this. Let's suppose I have positive plate here, and I have, let's say, 1 unit charge, that is like equal to electronic charge, okay, positive charge, and then you have a negative plate, let's say with negative charges, and the potential difference between these two plates is V. Okay, now if I let this charge go, then it'll move towards the negative plate, right? Okay, so it'll move towards a negative plate, so then it'll get some kinetic energy. All right, it'll gain some kinetic energy because it's getting faster and faster and faster. It will accelerate towards a negative plate. So if I make the potential difference V to be equal to 1 volt, then the work done on that electric charge will be equal to 1 electron volt. So 1 electron volt is equal to 1.6 times 10 to the power minus 19 coulomb, that's the charge, and times 1 volt. And that is 1 electron volt, or 1.6 times 10 to the power minus 19 coulomb volt. And that is 1.6 times 10 to the power minus 19 joules. So actually it's a conversion factor between electron volt and joules also, right? So this is just the unit of work, all right? So that's electron volt. Okay, so we are going to stop here for this video, and then next video I'm going to do a problem. Okay, I'll start from the same page.